Hi everybody, welcome to the summer colloquium. Today's speaker is Leon Ofman, and you probably all know him. Leon got his bachelor's in physics in 1986 and his master's in 1988 from Tel Aviv University in Israel. And he also got his PhD in physics in 1992 from the University of Texas in Austin. He held the National Research Council postdoctoral position at NASA Goddard from 1992 to 1994. And then he continues to work at NASA Goddard under various affiliations through industry and academia. And in 2009, he also became a research professor at the Catholic University of America. And his main research interests are solar plasma physics, MHD, waves and instabilities, kinetic processes related to coronal heat and acceleration of a solar wind. His main expertise is in numerical modeling of the solar coronal and wind plasma driven by space-based observations. So I'll leave it to him to continue.
Okay, thank you. Okay, today I'm going to talk about the origin of the slow solar wind. And this talk basically arises from a discussion held in an EC team workshop on slow solar wind that was held in Bern, Switzerland in the last couple of years. Now, for those of you who are unfamiliar, the EC is the International Space Science Institute that invites teams of experts for discussions of focused topics. And this topic, as you can see, there was a team of people from various institutions in the US and Europe, basically, and from China. And Luciano and myself were the co-leaders of this EC discussion. So, this is the outline of my talk. I'm going to talk about the in-situ observations of the slow solar wind. We'll discuss the slow solar wind sources in the outer corona as they are seen in white light and in UV observations. Then I will talk about the various contributions to the slow solar wind sources, the hypotheses or the physical models of the slow solar wind formations and their observational constraints. Finally, a summary and conclusions. So just to briefly remind ourselves, what are the typical parameters of the slow solar wind and how they differ from fast wind? So during a solar minimum, there is a clear distinction between slow and fast wind, where the fast wind is associated with coronal holes and slow solar wind is associated with streamers, but I will discuss this in more detail. As you can see, there is a difference in number density. The slow solar wind is on average 4 times denser than the fast wind, and the velocity is about half of the fast wind velocity. This could be 600 and up kilometers per second. As you can see, the proton temperature is lower in the slow solar wind, but the electron temperature is higher than in the fast wind. Then the alpha particle temperature is also lower than in the fast wind. You can see that the magnetic field strength is similar, is about 6 nanotesla at 1 AU. So that already suggests that we have different heating processes that prefer ions in the fast wind but are more uniform between ions and protons and electrons in the slow wind. So what do we know from in-situ observations? As you can see, there is data from the SWIX instrument on board Ulysses. This shows the FIB bias. That means how much of the low first ionization potential elements are abundant in the slow wind compared to the fast wind. And you can see that the low FIB elements are more abundant in the slow wind than the high FIB elements when compared to their photospheric composition. This is from von Steiger. Then the fast wind has a FIB bias of 1, 2, while the slow wind has a larger degree of FIP effect, on the range of variation of the FIP bias is much larger too. So that FIP bias, first ionization, that happens really very low in the solar atmosphere, somewhere in the chromosphere and the transition region, that tells us basically that this effect is much stronger in the slow wind, and it can be used to relate the origin of the slow solar wind to various structures and regions in the solar atmosphere. Now, the other effect that needs to be considered is the velocity of the alpha particles. Okay, and you can see here on this graph on the left, there is a strong anti-correlation between the velocity of the alpha particles and the freezing temperature. So, and this correlates with the compositional signature. So there is another effect that differentiates the slow solar wind. Okay, so as we know, there are regions where we measure the slow wind, and then there are fast wind. But then from Ulysses, we know that there are transitions, very sharp transitions between the slow and fast solar wind streams, and they are evident here in the velocities, as you can see here, and this is the various ion ratios. For example, one measure that is used is the ratio between oxygen 7 plus and oxygen 6 plus. Sorry, the labels are a little bit small. Okay, and then the other element is the carbon, okay, which is the carbon 6 to carbon 5 plus. So the transition boundary is very sharp between the slow and fast wind. Well, in the corona, when we look lower down in the corona, the transition from fast and slow is not as sharp. So we see gradual transition, and this was basically obtained by looking, for example, at the outflow speed in the various structures that can be compared to where you see the fast and slow wind from UVCS measurements and from LASCO data. This is as function of the solar radii. So basically, the UVCS uses spectroscopic methods. For example, if you have an effect like if you have a doublet, for example, from oxygen, that is flowing out, there is a Doppler shift of the various parts of the emission, and then the ratio between the doublets is called Doppler dimming, can tell us how fast this ion is flowing, because the Doppler effect would cause one of the doublet lines to be in resonant more with the emission coming from the chromosphere, and the other one would resonate less depending on the shift. So that could be used to measure the outflow speed. The other thing is from LASCO, which I will discuss in more detail, where one can measure the outflow of the blobs, and that can be seen also as the slow solar wind speed. Okay, if we look at the in more detail in what happens when the slow solar wind arrives at 1 AU, we can look at turbulence and magnetic fluctuations. But these fluctuations, as shown here, as a function of frequency, tell us that there is more energy in the low frequency fluctuations, and then there is, of course, the energy decreases very rapidly. The scaling, if you look at the scaling of this power law, is f to the minus 1 in the low frequency range, while in the high frequency range we have something like 5/3, which is indicative of turbulence. Now the breakpoint, the location of the breakpoint as a function of frequency depends on the distance. So as the solar wind moves out, then of course the magnetic field strength drops, and these structures, so the transition occurs at lower frequencies. So that is very suggestive of the kind of process that may hit the solar wind. The other issue is the kinetic temperatures. So if we look at the diagram where we place the anisotropy, the difference between the or the ratio between the perpendicular and parallel temperature of protons in this case, compared to the direction of the magnetic field as a function of plasma beta, which is the ratio of thermal and magnetic pressure, we can see this typical shape, diamond-shaped structure. And the question is, why do we see this typical structure? So it turns out that the boundaries of the structures line very well with kinetic instability. So, for example, on the left, there is this is the ion-cyclone instability, and this is the parallel fire hose instability. On the right, these are the same data, but now we plot different instabilities, which is this is the oblique fire hose and this is the mirror instability. So basically, what this strongly suggests is that if we have a plasma that falls outside this range, for example, we produce plasma with this high anisotropy and high beta, then very quickly it will relax to this state. So when we measure, we already measure the relaxed state of the plasma where all these instabilities, if they occurred close to the sun and took out this parameter space. So this suggests that the kinetic instabilities have a strong role in shaping the distribution of the plasma as we measure at 1 AU. Now, in order to understand the solar wind, we need to relate, of course, to the sources of the solar wind. But the problem is that we look at different sources by tracing back our sort of flux tubes to the solar surface, and then we still see similar solar wind speed. So here's an example. This is a study by Ko et al. So what you see here, this is basically a magnetogram, and this is the 195 emission. And these circles here, the yellow and the blue, show the sources that are then traced to Ulysses. And you can see that in some cases you do see the transition between the various quantities, like the outflow speed, but the transition, or in the charge state. But sometimes there is no clear transition between these states, and it's not clear that you can relate the slow and fast wind to these structures. So it turns out.
Can you say something about how you know those are the sources?
Well, basically, they are traced by looking at the various flux tubes and what is the charge states that are there, and then it can be they are traced back. But of course, it's not accurate. It depends on the model, on some expansion model, let's say PFSS, Lang-Sheely-Argy model type of structure. Okay. Now, it turns out that a better way to differentiate between the slow and fast wind is to look at the ratio between various ion abundances. So if you look at the carbon 6 plus to carbon 5 plus ratio and construct a diagram versus the oxygen 7 plus to oxygen 6 plus diagram, it turns out that this line that is approximately at the product being equal to 1% tells us that this is a slow and fast wind. So this is very good differentiation, although in some, this is from Ulysses measurements. From ACE, there are cases when it doesn't work as well, but it turns out that the speed alone is a poor differentiator of the speed, of the type of the wind, and the ion abundances and the charge states is a much better differentiator of the slow and fast wind. So, what are the slow solar wind sources? If we look in the outer corona, okay, of course there is a question how it is produced lower down, but then as the plasma leaves the lower corona, it propagates in the various structures. So here you see a schematic representation of a coronal streamer, and this is a coronal hole. So we have this region okay, where we have an interface between closed field lines and open field lines. And then you can see that plasma, of course, can escape along this open field into the heliosphere. And this region is a possible source of that slow solar wind plasma. However, there is another source, and that is the cusp of the streamer, because here we can have reconnection going on, and I will mention it in more detail. And you can have blobs of plasma escaping into the heliosphere, carrying some of the closed field plasma. Now, another possible source is if you have like multiple streamer structure, you have these, again, corridors of open field that are open to the heliosphere, and then again, plasma can be carried and connect through the heliosphere. A possible sort of structure that can explain this is the S-web model developed by Antiochos et al., which basically tells us where the fields are compressed and closed, and in which fields they are open and can connect to the heliosphere. There is a structure called pseudostreamer, which again contains open field region. And the difference between a pseudostreamer and a regular streamer, this is from Riley et al., is that in a regular streamer you connect between opposite polarities. So these field lines basically are closed between plus and minus the magnetic field. And then you have this boundary where the solar wind can flow. In pseudostreamer, basically you have the same polarity. So these field lines, the open field lines here, have the same polarity, while here they have inverse polarity. So basically this streamer is forming from a quadrupole type structure where you have maybe some closed field inside, but then you have a channel where the plasma can escape. Now, of course, with the line of sight effects, it's difficult to distinguish between the various structures, and that's where you need 3D modeling, because it would be observationally hard to distinguish between a pseudostreamer and a regular streamer. Now, from white light observation, going back to the question of, or to the point of reconnection, here's a schematic representation of this process. So you have some closed field that then is stretched, and then you have some reconnection going on, and then you have a plasmoid emitting the plasma, and in the stock of the streamer you have outflow of this plasmoids. This is modeled by Lang et al. 2000. So this was measured for the first time using LASCO data, where basically these blobs were traced to about 30 solar radii, and one can then make a diagram of the distance versus velocity and obtain, on average, a speed profile, and that is very typical speed profile of the slow solar wind, as one would expect from, for example, Parker's solution. So since then there were more detailed studies. This is from stereo. Again, one can look at these blobs. Now, of course, with stereo, the advantage is that there are two field of view, so one can identify these blobs. And in some cases, they appear to be, from one view, they appear to be as blobs, but from another view, they could be elongated structures. So indicating there is like a streamer belt or an arcade that emits these structures. And this was a study by Vial and Worlidas that made these more detailed studies of the slow solar wind using Core 2 data. So, to summarize some of the white light streamer results, so these are basically heliospheric plasma sheets where we see the propagation of the blobs, and then consist of narrow rays that could be possibly formed by interchange reconnections. Now, if you inspect in more detail these plasma blobs, they are basically mini flux ropes, and this is became very evident with the stereo observations, as you can see it from the two views. Now, in the pseudostreamer, you can also have a plasma sheet, but there are no blobs because the field lines, since they have the same polarity, they do not reconnect, so there is no blob emission. However, there is still a channel of open field that can direct the plasma flow. So now what we know is that during solar minimum, the slow solar wind comes from rapidly diverging flux tubes just inside the polar hole boundaries, while at solar maximum, we see it from diverging flux tubes rooted in active regions. So there is a difference between minimum and maximum. So, and that is understandable because during minimum we have sort of a heliospheric current sheet and bipolar structure of the solar wind. There is very, very clear separation between a streamer belt, and coronal holes. So the region that the interface between the coronal holes and the streamers, the global streamer belt, can act as a conduit for the slow solar wind. So now, from the point of view of modeling, what can we do to understand better the formation of the slow solar wind? So the first is most simplified modeling approach is to use polytropic MHD. That means we solve the MHD equations, but for the energy equation, one assumes some polytropic index close to isothermal, and that index is determined empirically, basically based on the observation. So with this empirical polytropic index, we avoid the question of how the corona is heated, what are the losses, and so on, thermal conduction losses, radiative losses, etc., because this index empirically folds all these processes into the simplified energy equation. And this modeling approach provides some successes, at least morphologically. This is from a study by Mikic et al., where you can see eclipse images on the right, and this is the modeling that was done, the 3D MHD modeling for several eclipses. The date is listed below here. And you can see that globally the agreement is nice, one would say. But when looking in more detail, we can see a difference. Part of it, of course, comes from the fact that we don't have proper boundary conditions of the lower corona, since we obtain the magnetic field only through a Carrington rotation. So, of course, there are some models that try to overcome this issue, but we don't know simultaneously from one view the proper boundary conditions. The other is with the polytropic index like this, the thermodynamics is only approximate. So, for example, if there is a strong heating in one of the streamers that causes this to expand or increase in brightness, that will not be properly modeled with a polytropic model. On the other hand, we don't know the details of the heating. We can sort of work back from the structure to the corona, but not as a forward modeling. So the other effect that needs to be considered is as you see from the result of that, is the heating process. So the heating process, there are various candidates. One of them that I'm particularly interested in is the wave heating process. So we do have observations now from many instruments that show the presence of waves, MHD waves, throughout the corona. But the one I want to discuss today is the evidence from the ground-based, from the COMP instrument. And as you can see here, for example, here shows the Doppler shift variations in the lower corona as it's observed. And there is a line width as well, I see here. So there is evidence, this can be interpreted as evidence of waves. There is resolve velocity fluctuations as well. And we see that the frequencies of these fluctuations are in the range one would expect in the corona, given that there is a very strong driver below from P-mode oscillations. So it's in the 3 to 5 millihertz range. However, the amplitude from this data is quite low. The phase speed again agrees well with what we would expect in the corona, between 1,000 and 5,000 kilometers per second. So since the fluctuations are perpendicular to the line of sight, as they're seen here, so they are evidence of some alphanic fluctuations that could be kink mode, which is basically a form of a fast MHD wave in a structure, but there could be also torsional Alfvén waves, or in the case of arcade, these Alfvén waves could be shear Alfvén waves, basically. So ignoring for the moment the question, of course, of the amplitude, we don't really know if the amplitude, the low amplitude is a result of limitations of resolution or line of sight integration. We can model the injection of these waves using an MHD model. So here are some results that I've done recently of this modeling. So what you can see here on the left is the structure of the streamers. This is the outflow speed. It's normalized in units of the Alfvén speed. So you can see the bright regions, this is where the faster wind is, and the slower wind is here in the stocks of streamers. Inside the streamer, the velocity is very low. And then, in addition to that structure, we injected these waves, or in the model, I've injected waves. As you can see, in the closed field region, the shear Alfvén waves are trapped. They cannot reach the open field region because they cannot propagate across the field. They can only propagate along magnetic field structure. But in open field, in regions where we would expect the fast wind, the shear Alfvén waves, they propagate outwards. And you can see the currents associated with these waves. These are the velocity fluctuations, magnetic fluctuations, and the currents. And here, this is the log of the electron density. So this is the magnetic field in the radial direction. So you can see that there are current sheets, small-scale current sheets associated with these waves. So these waves produce these current sheets that are propagating as well, and they can deposit their energy, basically dissipate and hit the plasma. But the problem is they're not going to reach this region. There's nothing here because of the nature of shear Alfvén waves as they propagate along the field.
Are these difference maps subsequent times that you subtract from each other, or what are you?
No, this is because this is a model. This shows the cut or basically this is 2.5D. So this shows the plane, the theta R plane of the components, okay, of the various components. So.
But there's a strong average that is clearly subtracted then.
Sorry.
There's an average value of the velocity.
Yeah, this is a snapshot at a given time. So if one wants to translate it to WKB, then one needs to average over time. But this is a snapshot that gives you the actual velocity fluctuation as the wave. Yes.
So you subtract that from the average.
Well, there is no average V phi in this case. The V phi is 0. In this case, just to explain. Okay, this is the radial outflow. So here you don't see the fluctuations because the radial outflow is quite strong. So indeed, if we subtract, we may see some evidence of that. But in this case, because in a 2.5D, the outflow is basically we have two components. We have VR and V theta. So V phi, the component goes out of the board, is 0. Okay, so this is just the fluctuation. This is only due to the wave. That's why it's 2.5D. Okay, so here is an animation that shows the V phi component at various times, and you can see the waves as they propagate. Now the waves are launched in little segments here with random phase, so sort of simulate as what would happen if we have many sources due to the fluctuations in the lower atmosphere leading to the injection of these waves. The amplitude is quite small. It's only a few percent of the Alfvén speed at maximum. Okay, of course we can also experiment with injecting fast magnetosonic waves. And in that case, the picture is a little bit different, and because the fast multisonic waves propagate across the field. So they don't have the limitation of the shear alpha waves. And you can see here, now this is indeed subtracted, background subtracted density. You can see the perturbations produced by the waves, but they now propagate inside the structures. And this is the radial velocity. Okay, again, you can see the fluctuations here going in open and closed field regions, because the waves can now propagate more freely in the closed field region. There is still, so now you can see that from the density fluctuations that these waves propagate primarily in the closed field, or they cause the density perturbation in the closed field region. So, of course, we are now exploring the parameters of this model, but the difference between this model and other global models or 3D models is that we drive the wave explicitly, so we need to resolve the scale of the shortest wavelength. A different approach would be is to inject a WKB waves, where we don't actually resolve the waves, but provide some pressure term essentially, and another energy equation or transport equation from the waves. And this has been done, this approach has been used for quite a while. Here is a recent result from van der Hulst et al. This is the SWMF model, so they have the WKB alpha wave term, which then allows them to produce the fast and slow wind, as you can see in these several images, and then also produce some improvements over their synthesized emission lines. So now going to the ion emission, because we mentioned ion emission, you can see that the streamers look dramatically different when you look at them at different emissions. So for example, what is shown here, this is the Lyman alpha H1 emission, and then you can see the emission from oxygen, the oxygen 6 line and the magnesium 10 line. Okay, and you can see that the streamer here looks like there are two streamers instead of one, and the same in the magnesium 10 line. So one tries to understand this question: why do we see completely different structure in these emission lines? And one of the possible explanation for this phenomena is because of the fact that there is a solar wind outflow along the boundary that changes the abundance of these heavy elements in the legs of streamers. Okay, and then the stock still shows outflow, but of course it is already weak in all lines. But inside the streamer we have gravitational settling that decreases the abundance of the heavy ions. So now, how do we understand that? Okay, from a MHD model, we have single fluid, so it's not really possible to distinguish between the dynamics of the heavy ions and the helium. So in order to do that, one needs to solve the three fluid equations. This is sort of the next step in plasma approximation, from the next step from MHD. So instead of having just one continuity equation, we have basically three continuity equations, right? In this case, since we neglect the electron inertia and assume charge neutrality, and we have two equations of continuity, the electrons come from the charge neutrality. And the Ohm's law comes from the fact that we neglect basically the left-hand side for the electrons and then solve for the right-hand side. But we still have three energy equations, and we have two momentum equations for each ion species. Okay, since we assume that the interaction between the heavy ions themselves is weak, we can limit our model to 3 fluids. Because if we had the 4th fluid, the interaction between the 3rd and the 4th, due to the properties of the corona, of the low abundance of heavy ions, would be small, maybe negligible. So then the thing is that there are several complications compared to MHD. First, you have this term here, okay, and if you inspect this term, you can see that this is basically the ion gyro frequency, which is very high in the corona, right? So in principle, we would need to resolve the gyro motions of the 2 fluids, of the 2 ion fluid, and that would be difficult. So one can make some approximation of averaging them out if you don't have under certain conditions. Okay, then we have the Coulomb friction term between the various fluids, and this is a very important term for understanding slow solar wind, but one needs to calculate all the collisions between, all the binary collisions between the fluids. And then in the energy equations we have this, now it's energy equations, not equation, because we have 3 of them, and then we have this coupling term. So just to give you sort of an idea, we need to include all these Coulomb interactions and the difference between the speed in the ion fluid, electron fluid, proton, ion fluid, and so on. So these are all calculated explicitly, all the collision terms calculated in the code, and then the energy exchange terms, as you can see here, they are also calculated. So if we have some temperature differences between the ion species and the electrons, then they would equilibrate if the collisions are strong enough. So in the very low corona, they would very quickly equilibrate. So let's say we start our model with a low electron temperature and very high ion temperature. Then in the streamer, they are very quickly will equilibrate. But as the model extends to several solar radii, and the collisions drop off rapidly, since they depend on the density, the electron density and the ion density and so on, then these terms will not act anymore. So then that temperature difference could be sustained at larger distances. So here are some solutions with the multi-fluid model. And you can see here on the left, this is what is seen. This is the solution, the density of the protons, ionized hydrogen. Now, and on the right you see the result where the 3rd ion was helium. So you can see this typical structure of the 2 legs compared to this more uniform streamer structure. These are the outflow speeds of the ion. So there is some diffusion as well at the y point of the ion into the streamer, and there is gravitational settling of the heavy ion. Now this is the electron temperature. Again, it peaks in the center, as you can see, and decreases outside the streamer. Now for oxygen 5+, we see a similar structure as we see for the helium. And it turns out for any heavy ion, we would see this type of bifurcated structure compared to protons. Okay. Now, because we know from UVCS some line broadening results that tell us about heating of these heavy ions, we can model this by introducing some empirical heating. So what you see here is the result of such a model that has empirical heating of oxygen. This is the oxygen temperature. But it turns out that because of the collisional interactions inside the streamer, okay, with electrons and protons, even though you heat the oxygen 5+, it's very abundant, with very low abundance, it cools very quickly due to those energy exchange terms. So inside the streamer, the temperature of the oxygen does not increase that much as outside the streamer. Outside the streamer, where the density is lower and collisions are less, there is more dramatic temperature increase. So even though we heat the oxygen plus ions uniformly as a function of latitude, the collisions provide the latitudinal variability between the various structures. Okay, and these are this is the proton, corresponding proton temperature, proton density, electron density. And we can do the same exercise with magnesium 9 plus. Okay, and we can see the same result. So even though we heat this magnesium very strongly, okay, now the scale is determined by observations. So you can see that there is strong cooling inside the streamer. But of course, collisions are less for magnesium 9 plus, so the cooling is less dramatic than for oxygen. Now, what do we see from observations? And you can see here a cut of UVCS data, and they show these dips. So you can see this is the blue line is the proton emission, or neutral hydrogen in this case, and then you can see this dip in oxygen emission and as well as the magnesium 10 lines. So one can compare, this is on the left, their modeling results. Now these are the simulated line emissions by calculating the actual collisional and resonance scattering, and this is the comparison. And you can see the asymmetry that we see from the data, and I will get back to that, discuss this asymmetry. So this was a study we published where we made a detailed comparison of the various quantities like the outflow speed, the density, and the kinetic temperature at various distances. So the top is at 1.54 solar radii, and this is 2.2 solar radii. This is where UVCS can measure. So these are the proton and electron temperatures. As you can see, there are two lines here. There is a solid line and a dashed line, but they are nearly identical. So in the slow wind, the collisions are frequent enough. So low in the corona, we're talking about up to 2.2 solar radii, there is practically no difference. So the heating function was affecting the oxygen. So you can see the higher oxygen temperature. Now, again, we chose the parameters of the heating function to match these values inside the streamer. But you can see that outside, of course, it can increase due to the lower collisions, and this is at 2.2 solar radii. So there is quite a good matching of these quantities. You can see also for the outflow speed and densities, normalized densities. Now, using the collisional and resonance scattering, one can calculate the emission lines, and of course you have to take into account Doppler shift and so on. So one can compute the emissivity maps based on the results of the multi-fluid modeling. And now we are trying to do a similar thing with forward coder with Sarah. So the idea is that we, instead of computing the ion abundance or the heavy ion abundance based on Chianti data, we can use the actual output from the model in order to get the emission lines. So this is the result, and you can see here, this is the model, this observation. Of course, there is a difference in the scaling, but qualitatively they look very similar. This is the proton, and this is the oxygen, and you can see the asymmetry, which I will explain the source of this asymmetry. What we just to explain briefly, this is the result of the 3D structure of the streamer. So in magnesium, we don't have as many points. There are only a few points available. So because of the very low emissivity of magnesium, the VCS data were average, so there is only 1 point inside the streamer. But there is some radial dependence, so we can fit our empirical heating function to produce, for the heavy ions, to produce this temperature structure. But then the rest of the dynamics will be due to the collisional coupling and the effects of the expansion and so on that will produce the properties of the ions. So now this is the radial dependence. So again, compare the normalized radial dependence is very similar from the model and observation. This is from magnesium-10, 625 angstrom, and this is the H1 Lyman alpha line. So this has been published in MJ. Now, recently we extended the model to 3D. So what you see here is the tilted dipole model. Again, the model goes to several solar radii. It's not a global model intended on predicting space weather, but this model's goal is to understand the source of the slow solar wind. So you can see here sort of the Carrington representation of the proton density, the ion density, ion temperature, and the radial outflow speed. This is at 1.5 solar radii. So you can see at 1.5 you have this difference in the density structure inside the streamer, which is high compared to the outside, and the inverse structure for the oxygen. And this is the temperature structure. Again, you can see higher temperature outside the streamer and lower inside the streamer. And this is the radial outflow speed. So one can look at the cut in the R theta plane, and we can see that we reproduce very nicely the results of our 2.5D modeling, although now it's a tilted dipole, so the stalk of the streamer is not exactly in the center, depending, of course, where you take the cut. It will be shifted towards the center. So we can see the oxygen density with lower density inside the streamer. This is the proton density, this is the electron temperature, and this is the ion temperature, and this is the outflow speed, and this shows the current sheet that is surrounding our streamer structure. So we are now confident in our 3D model, and we started to implement a more realistic field, PFSS field. We have some preliminary results that are encouraging, that shows that we can reproduce some of the observed streamer structures in more detail. Okay, so now regarding the asymmetry that we were discussing, so you can see here, this is the result of a line of sight integration of the tilted dipole model of the three-fluid streamer. And this is the H1 emission line, and this is the oxygen 6 emission line. And if you can see this, there is variation in emission as the structure is rotating. So what happens here, because of the integration of the line of sight, we see that depending on the angle, one of the legs of the streamer becomes brighter in the oxygen 5 plus emission, or oxygen 6. Okay, but of course the effect on the H1 is smaller because the line of sight doesn't affect the, just affects where the center is of the emission, but does not affect the structure, still quasi-Gaussian structure. So you can see this effect, which we've seen in the 2.5D, it was not possible to explain this effect in 2.5D, but when one takes into account the tilted streamer structure and the line of sight integration, then it becomes very clear. So clearly 3D modeling is very important for understanding the streamer structures and the line of sight integration. This is the streamer as it's seen here. As you can see, one foot is stronger than the other one. Okay, now let's review the physical parameters of the streamer. So again, if we look at various parts of the streamers or in the coronal holes, you can see that there is a strong variation of the electron density and the temperatures, especially for the heavy ion. So you can see here in this graph, you can see that the heavy ion temperature in the coronal hole regions and in open field regions is much higher than in the streamer regions. And this is MHD, an MHD model where it allows you to identify those regions. But of course, it's not sufficient to understand this variability in the temperature of the heavy ions, and that requires really a three-fluid model. So there were plenty of UVCS observations that are summarized in these two graphs. So on the left you can see temperatures in the various regions where the coronal hole regions tend to be hotter while the slow solar wind regions are cooler. And this is the outflow speed, again summarizing the various regions from a number of studies that's showing you the outflow speed based on the Doppler dimming effect, for example. So now we want to connect between the sources of the slow solar wind and active regions, since we know that at solar maximum the active regions are associated with the sources, and this was done by Hara et al. And Brooks et al., where they looked at recently at Doppler emission. So basically, and the FIP effect. So basically, the Doppler emission tells you that there's a blue shifted regions in all of these active regions, indicating that there is some outflowing material, and this is the FIP effect showing where the regions are stronger. So that can, from ICE data, can also provide you the sort of the boundary condition or the sources of the slow solar wind. But of course, because ice looks very, very low, some of these outflows can be in confined regions. It's not clear that all this plasma is indeed escaping to the heliosphere because of the closed field. So it's just, we're looking at the plasma at that temperature when it's heated as it goes up, but we don't see evidence of the cooling in those images. So we can summarize some of the observational constraints on the modeling of the slow solar wind. So we have UV and white light images that shows that there is a topology of expansion of streamers, and then you have dynamical emissions of blobs. Then we have spectroscopic constraints that shows you the outflow speed from the Doppler dimming effect and the temperature anisotropy. Then we have in-situ constraints that tells us about the ratio between the various elements, elemental abundances, and FIP effects. Finally, we have the temporal variability that we see and the magnetic field measurements. So all of these must be reproduced or constrain the models that we use. So far, our models are limited, but one can summarize, okay, in general, what we see about the slow solar wind. So first, we have the several hypotheses that are summarized here of the slow solar wind formation. So you have some interchange reconnection between the closed and open field that results in the plasma escaping into the open field. Another hypothesis is blobs. Okay, so again you have some reconnection going at the y point, and that emits these blobs. Now we have, this is another form, this is the S-web, so it's also a form of reconnection where we have open and closed field that are connecting and then resulting in emission of the plasma. But in all of these regions, we need to understand the heating where, for example, it could be wave heating or some turbulent cascade. And this is especially important in the open field, but also in the regions that connect the open and closed field. So we need to see if the hypothesis of solar wind formation are consistent also with the observations that we see. So whether we get the type of plasma and the type of FIP effect that we would expect from the various processes in the solar wind. So just to summarize, sort of course, we have two upcoming missions like the Solar Orbiter and Solar Probe, and they will allow us to get some important information on the slow solar wind. The Solar Probe has the advantage of being out of the ecliptic at part of its orbit, so one can transition between the slow and fast solar wind, and one can see the evolution of the streamer belt due to the co-rotation as the spacecraft will move fast so that it will remain in the same structure for some time. So it can detect the evolution of the streamer belts. Then there will be important instruments like the METIS and the SPICE instrument that will observe the corona spectroscopically and also study the SPICE instrument will detect the actual ions, so one can correlate together with the corrotation. One can correlate it much better than today. That was relating to your question on the sources of the solar wind and where they are as they reach the observatory. So there is some perspective of combined solar probe and solar orbiter observations, so I'll leave it for next time. And to summarize, so the main sort of conclusion that came from the discussion at the EC workshop was that it's not possible just to classify the type of the wind based on speed. We need to understand the elemental abundances and the charge states, and they provide a much better ways to classify the solar wind. And then we can, of course, need to consider various processes of solar wind formation, like the reconnections blob or just heating where you have a outflow in open field. That would provide sort of relate the sources of the wind and the properties of the sources to the actual plasma that we measure. And this is really is required in order to understand or to determine which of these processes is the dominant process that produces the solar wind. And this sort of review is going to appear in Space Science Reviews. It's already been accepted, so you can read in more detail the details of these discussions. Thank you.
Any questions?
So when you showed the observed wind spectra at different distances, 0.3 and 0.9 and 0.7, I was surprised that the breakpoint was actually different at different frequencies, whereas the scale was actually the same in the vertical axis. So these three different breakpoints have the same vertical breakpoint, but very different horizontal breakpoints on the graph. Do you know why that is?
Well, the breakpoint that I showed you relates between the large-scale structures and small-scale structures that are formed due to turbulence. So the large-scale structures are coming from the sun. So their scale is determined by the source. And then as they propagate into the solar wind, there is turbulence going on. And as the field becomes weaker, the frequency where the turbulence becomes important becomes lower and lower. So that is the effect that is seen here. But there is variability of the frequency, and the energy varies a little bit less, but there is a scaling as well for the energy.
Yes, yeah.
Anybody else? Yes.
I have a question about the bias, fit bias.
Yes.
You mentioned the difference of abundance between slow solar wind and fast solar wind. I still do not understand why it's different in abundance.
Well,
Slow and fast solar wind.
At the ionic level or the atom level?
I mean,
well, basically, okay. Let me step back a little bit. So you have in the photosphere you have certain heavy ions, yes, and these heavy ions, then there is certain ratio we can determine it spectroscopically, right? Now, as the plasma gets ionized, some ions are preferentially accelerated.
yeah.
Okay, and
is different between slow wind and fast solar wind?
well, what it suggests that we have different acceleration process and heating process.
So plasma know he will go to the fast solar wind or slow solar wind in the photosphere.
Not in the photosphere. It's where in the. Yeah. You want to?
No.
Okay. So it's not in the photosphere. The thing is that as the plasma gets heated somewhere in transition region, chromosphere, in transition region, it gets heated. So then it gets accelerated. So depending on the process of acceleration, right? For example, if you have a process that depends on the charge to mass ratio, yes, then the ions that can be ionized first, they can be accelerated more, and they will end up, more of them will end up in the coronal plasma. So the heating process, one of the suggested sort of process was Alfvén waves. This is Laming's idea. Okay, so you have Alfvén waves that generate ponderomotive force. Okay, basically electric field parallel to the direction of the magnetic field. So then, if the ion is already ionized at some temperature, some low temperature, that the ion that is ionized first will be accelerated more. But that would depend again if this plasma can reach open field or is it stuck in a closed field. So in a closed field, you will have different rates of accumulating these ionized elements. And then only when they connect to the open field, you will get them in your slow solar wind. So that the Fib bias there is larger. But this is just hand waving. Of course, one needs to do a detailed calculation. I think there are some, but there is. I would not say that this problem has been resolved yet fully.
I think a philosophical question.
Sure.
The fast one is probably a lot easier.
Fast wind is easier because we have a predominantly open field. So it is easier to distinguish, between the zoo of processes. Now, when we talk about closed wind, we have interchange reconnection, blobs, acceleration, open field line, expansion factor. So there are several mechanisms that could act together. Now, in open field, we have some variation in the expansion, but otherwise, if we consider this strictly open field, then that limits the number of processes, and that sort of points us towards wave processes and kinetic waves as well, like Hans-Acton waves.
Yeah, because fast one characteristics are pretty much the same for almost all coronal holes in almost all types. That it's kind of like almost like you're seeing the DNA of the basic fundamental process.
Well, there is some variation between equatorial and polar coronal holes. So in equatorial holes, although you would expect it would be similar to the fast wind, but it looks often like the slow wind as well.
June had a question.
Yeah, so the active regions, they have stronger fields, they're denser, they're hotter. What are the characteristic differences between slow wind from active regions, slow wind from, say, around a streamer? And how do you see that kind of a difference between solar min and solar max when there's lots of active regions versus none?
Well, if we are looking about, again, as you can see from this graph on the left, it turns out that the best way to distinguish is between the slow and fast wind is by looking at the ratio of the abundance.
Slow and slow. Slow from active regions, slow versus other.
Right, so this is still an open question. As I showed you, you can look at different regions. Some of them show difference, some of them show similar signatures. So this is still an open question. Which one of these processes was the dominant one? And there is no clear way to distinguish, and that's where we hope the solar orbiter would help, for example, by directly relating, by sitting in one structure as it co-rotates and looking in that streamer with the SPICE instrument at the various abundances of the heavy ions, and then maybe one can relate more accurately and distinguish between active region wind and just very rapidly expanding flux tube wind or a blob wind. But it's not, because they come from similar plasma, these processes is not as easily distinguishable.
Anything else? No. Thank you very much again.